Hello and welcome to Physical Attraction. In this episode on our series on cosmology, we're going to be talking about Einstein's cosmos. When it comes to understanding how physics has developed over the years, it's crucial to understand the interplay between theory and experiment. Remember that theory in physics really refers to the framework of mathematics, concepts and ideas that we use to explain and predict future observations. So for example, Newton's theory of motion, or the general theory of electromagnetism, and so on. Theory and experiment seldom advance in complete lockstep with each other. Sometimes a physicist comes up with a theory that hopefully explains some properties of reality, some aspect of physics. Then, hopefully, as part of that theory, an experiment can be designed, which can be conducted to test properties of this theory. At other times, an experiment will occur which creates some new observation which the theorists then have to try and explain. At different points in history, and for different disciplines in physics, theory and experiment might be at different points in the race towards a general understanding. A classic example would be how our theories about light have developed over the centuries. Back when physicists were trying to understand the nature of light more exactly, they considered that light might need to be transmitted through a medium called the ether. This did make some intuitive sense. Observations had suggested that light behaved like a wave. A famous experiment, Thomas Young's double-slit experiment, demonstrated that different waves of light could interfere with each other and cancel out. But if light was behaving like a wave, then what was waving? This was the idea that gave birth to this concept of the luminiferous ether, a material, a medium that would carry light waves through its vibrations. Then the Michelson-Morley experiment, of which more another time, demonstrated that light could in fact travel through the vacuum without needing an ether, and that the concept that we had about the ether was wrong. So you can see how in history this interplay sometimes works. Young's double-slit observations and other experiments that made light appear to be a wave, these things led theorists to develop the idea of an ether to explain how light could behave as a wave. Then, to test the ether theory, Michelson and Morley devised their experiment. When this and other later experiments discredited the ether theory, it was necessary for scientists to develop another theory to explain how light behaved, which turned out to be Einstein's special relativity. And then some of the predictions of Einstein's special relativity have once again been confirmed by experiments that came after him, and so on and so forth. So in some ways this means that there are several different kinds of experimental result that can show up. You can have experimental results that were aiming to prove a theory correct, and succeed in doing so, like the much celebrated discovery of the Higgs boson at the LHC, which confirmed the predictions that a Higgs particle would exist, which go right the way back to the 1960s. You can have experimental results that aim to explore a theory that end up disproving the theory, or requiring the theory to be modified to make sense, like the Michelson-Morley experiment. And you can have some experimental results that arrive before the theory is ready to explain them, which leads to new developments where theorists try to explain the result within a framework that allows them to make other predictions and test their new theory. Don't take it from me though. Edwin Hubble, who we spoke about in the last episode, wrote this in his book, In the Realm of the Nebulae. He said, quote, "Many theories are formulated, but relatively few endure the tests. The survivors in general must be occasionally revised to conform with the growing body of knowledge. The ability to theorise is highly personal. It involves art, imagination, logic, and something more. An outstanding genius may invent a successful new type of theory. First-rate people may follow the lead and develop other theories on the same pattern. Less competent minds are embarrassed by the custom of testing predictions." End quote. And this was Hubble trying to be modest for once in his life, because he considered himself to be one of the less competent minds who was embarrassed by the custom of testing predictions. So in the last few episodes, we've talked about a bunch of astronomical observations that changed how we perceive the universe. We've discussed the observations that suggested that nebulae were really galaxies like our own galaxy. We've talked about observations that have allowed us to understand the scales of distance in the universe, and the relative velocities between us and distant objects in the form of redshift. We've discussed theories surrounding whether the universe is expanding or not, and if so, how it began. And we talked about Hubble's observations, which for many conclusively demonstrated that the universe was indeed expanding. One of the interesting things about the era of cosmology and astrophysics we've been talking about in the 1920s is that a lot of the observations did arrive within the context of a theoretical framework that had been developed over the past few years. For the first time, there was a theory of how the cosmos and the universe at large might behave over time. There was a theory, related to the theory of gravity, that would explain how the large-scale structure of the universe as a whole might behave, and how we might understand what it would mean for the universe to be expanding, which Hubble's observations slotted right into. This was, broadly speaking, Einstein's theory of general relativity and the field of theoretical cosmology that it opened up. So it's time to dive into it. Einstein obviously looms extremely large, both in physics and as one of the few physicists who has really crossed over into the popular culture. His image, his theories, and his name have become bywords for revolutionary genius. Clearly, at some stage, Einstein is worth his own series on this show. So rather than turn the Cosmology series into the Einstein series and mire myself in another hole which will take many episodes to dig out of, I will pick up the story halfway through and just describe the bits that directly relate to the birth of theoretical cosmology. And the entire Einstein saga, I'm afraid, will have to wait for some episodes in the long-distant future. So I don't want to get into relativity in full here, because I would shortchange it massively or go off on a really extended tangent that takes in most of physics. So this will have to be another topic for later. But what we will say is that Einstein's general relativity arose from some considerations that came from special relativity. The point of special relativity had, largely speaking, been that if you're an observer, if you're a person, if you're an experimentalist, if you're anyone, moving at a constant velocity, you shouldn't be able to tell any differences between the state of being at a constant velocity and being at rest. Imagine you're flying at 10 miles an hour in a certain direction. To you, this should be indistinguishable from the countryside rushing at you at 10 miles an hour. The laws of physics will appear to be the same if you're in either case. If you consider yourself, for example, imagine yourself in a train. If you board up the windows, you can't see what's going on outside, and the train isn't bumpy or accelerating, you won't be able to tell the difference between being at constant uniform motion and being at rest. If you are playing around with experiments within the train, if you've got a mass on a spring, if you've got balls that you're throwing around in different directions and observing things like projectile motion and so on your train that's travelling at a constant speed, you will find that the laws of physics behave exactly the same as they do in the outside world. Now, the marvellous consequences of this simple idea that if you are moving at a constant relative velocity to another observer, you should observe the same laws of physics. And the idea that there is a universal speed limit in the universe, which is the speed of light. These simple ideas, the consequences of them, that's the foundation of special relativity, which I think we'll have to leave again for another time. But to help explain special relativity, Einstein and others introduced four-dimensional space-time, so we live in 3 dimensions of space and 1 of time. General relativity essentially expands this to include an equivalence now between gravity and acceleration. In other words, imagine you jump off the top of a very tall building and you're in freefall. You won't feel the pull of gravity at all because you're accelerating towards the Earth at 9.8 meters per second. This is how astronauts aboard the ISS can experience weightlessness. They're actually accelerating towards the centre of the Earth as they rotate around the Earth in this geostationary orbit. To them, the physics that they experience in that freefall is indistinguishable from having no weight at all. And this is part of a broader equivalence that if you're accelerating in a given direction, your physics can be equally well described by having a gravitational field that's pulling you in the opposite direction. If you ignored air resistance, for example, for a free-falling skydiver or an astronaut, you would feel that there's no gravitational field at all due to your acceleration. What Einstein realised in general relativity, and again we're massively glossing over the details here, especially the mathematical ones, is that you can explain the action of gravitational fields by assuming that space-time is curved. The presence of massive objects, of matter with a mass that exerts a gravitational pull, is to curve and distort space-time in a particular way. Now, the classic analogy that people use here I am going to repeat for convenience, so apologies if you've heard it already. But to get some intuitive sense of how this actually operates, this idea that matter curves space-time and tells space-time how to bend, and that this is an analogy to the force of gravity. Imagine the world as a flat, two-dimensional surface, a blanket that's being pulled taut at each corner by a group of children. The kids are playing a game of 2D table tennis on the flat surface of this blanket. They're rolling ping-pong balls along the surface to each other. When they launch the ball in a given direction, it travels in a straight line to be intercepted by kids on the other side. So you can sort of imagine this as a kind of game of Pong, where they're all holding out this blanket, holding it taut, and launching these balls across the blanket towards each other. Then, to make the game more interesting, or out of a spirit of disruption, some kid grabs a bowling ball and throws it into the middle of the blanket. The kids can still support the blanket, but now it's sagging in the middle. Instead of a flat surface, you have a curved one, which is dipping down towards where the bowling ball is. And you can imagine that this would be a sort of convex blanket, right? You have the kids in each corners, they're holding the thing taut. You have the bowling ball, which is causing this big depression in the middle. And generally the rest of the surface has now become curved. Now the kids continue playing their game. They continue to launch these ping-pong balls across the surface. But now, when they try and launch them in a straight line, their paths will curve around the dip that is caused by this bowling ball. For some ping-pong balls, this means that their directions will change. They'll be sort of glanced by the influence of the bowling ball. For others who get too close or who aren't moving quickly enough, they'll roll down into the dip and stay there. And this turns out to be quite analogous to how general relativity explains the force of gravity. The presence of a massive object, like the bowling ball, actually curves space-time around it. And in turn, this means that the ordinary paths of the objects are deflected, as if by a gravitational force, simply by trying to follow a straight line in this curved geometry. This has also been summarised by the statement that space-time tells matter how to move, and matter tells space-time how to curve. Now, of course, you can think about this analogy and think about various different ways in which it does hold up and behave a lot like our understanding of how gravity works. Particularly, for example, you can think about things like escape velocity to escape from a planet, the amount of speed you have to be launched with so that you don't just roll back into that pit with the bowling ball. If the kids are shooting their ping pong balls a long, long way away on the blanket from where the bowling ball is, or if the bowling ball is quite light and doesn't actually cause that much of a depression, then you can imagine that there might not be that much deflection at all for the ping pong balls as they're travelling along their straight lines. Particularly if you launch them with sufficient initial speed that they don't actually curve and deflect. Then, of course, if they don't have enough speed, or if the bowling ball is particularly massive, you can imagine that some things might end up just being sort of trapped in these decaying orbits and curving round and round and round and round and eventually settling to be next to the bowling ball due to the force of gravity that is acting on them. And this is essentially the sort of analogy that you want to have in this case, except instead of the two-dimensional blanket being distorted by the presence of the bowling ball, it's actually four-dimensional space-time which is distorted by the presence of the bowling ball. And yes, both space and time are distorted. So not only is the trajectory of a particle of an object that is moving in a gravitational field, not only does the gravitational field change its trajectory in space, but also its trajectory in time. And this is very similar to the special relativity case, where the fact that we exist in four-dimensional space-time means that when we move, when we have a certain velocity, it alters not only our trajectory in space, but also our trajectory through time, through phenomena like time dilation. What Einstein realised, what he seized upon, was that actually there was a whole mathematical framework for these curved or non-Euclidean geometries. And that you could actually mathematically determine how the curved surface is going to look based on how much mass is present. And therefore you could determine the trajectories, the pathways that objects would take when they were travelling through this curved space-time. Obviously, relatively light objects like you or I, we have a minimal effect on curving space-time, and hence our gravitational influence on the world around us is tiny. The effect is much larger for much more massive objects, until you get into the realm of black holes, which are so compact that space-time becomes so hopelessly curved back on itself that nothing, even travelling at light speed, can escape from its gravitational influence. Once Einstein had derived these equations in which matter tells space-time how to curve, the really amazing realisation here is that this can be applied to the universe as a whole. Now, it's not fair to say that Einstein was the first person to try and link together this idea of a large-scale theory of gravity and trying to understand how that would lead to a different large-scale structure of the universe. In fact, these had been ideas that had been floating around for a very long time. But what they had found before, physicists and astronomers, they'd known for a long time that their theory of the universe was incomplete, because it would lead to apparent contradictions with the observations that they were making. And in fact, it had long been appreciated that gravity, this force that acts across vast distances, indeed across all of space in Newton's theory, could perhaps hold the key to the large-scale structure of the universe and how it evolved. In 1692, 5 years after Isaac Newton had completed the Principia and outlined his theory of gravity, he had a letter from a Richard Bentley, a theologian who was head of Trinity College in Cambridge, proposing a puzzling dilemma. Newton's theory of gravity said that gravity acted over any distance and was always attractive in all cases. Every object in the universe, however small the force may be, exerts an attractive force on every other object in the universe. But this, it seemed to Bentley, had disturbing implications for the universe itself. If the universe was filled with stars, then surely they would all attract each other and gradually collapse onto their collective centre of mass. The universe couldn't possibly be static or eternal, as Newton wanted to believe. Instead, it would be dynamic and unstable, eternally evolving towards some spinal steady state where the entire universe collapsed in on itself, dragged there by the force of gravity. This then raised all kinds of philosophical questions. I mean, for a start, you have to think about yourself, well, okay, was the universe created with all of this matter dispersed, and it's been collapsing ever since due to gravity? This creates an arrow of time for the universe as a whole, with the universe beginning in this dispersed state and then evolving towards this collapse. Now, this troubled Newton, but he thought that he had the resolution, and he thought that he could resolve it by saying, well, this implies that the universe must be existing in some way. It must have these properties. Newton decided that the universe must be an infinite collection of stars that were more or less evenly distributed throughout space. That way, they don't actually have a centre of mass, because whatever gravitational pull arises from stars in one direction would be cancelled out by stars from another direction, resulting in no net attraction. As Newton wrote, if the matter was evenly disposed throughout one space, it could never convene into one mass, and thus might the sun and fixed stars be formed. But this idea literally contradicted the evidence of our eyes. If the universe was infinite and eternal, and the stars were evenly distributed throughout it, then you run into something called Olber's paradox. In such a universe, no matter what direction you look in, there will be a star. In fact, there will be infinitely many stars at various different distances from you. The furthest stars might be fainter due to being further away, but they would be more numerous, infinitely numerous in fact, which would make up for it. If the universe is infinitely old, if it's this static eternal universe with infinitely many stars in any direction you care to look, then you can't explain this away by suggesting that the light from the stars in some direction hasn't had time to reach you yet. It would have done. It's had infinite time to do so. In other words, the night sky shouldn't be what we see. It should be a blazing, brilliant white light with starlight from all over the infinite universe in all directions. What we instead see is mostly darkness with a few pinpricks of light that somehow make it through the void to us. So despite this belief, perhaps rooted in philosophy, that the universe was eternal, static and infinite, the observational evidence was lacking. A question as simple as why is the night sky dark was a paradox that astronomers and cosmologists struggled to resolve for centuries. And it's just evidence, I suppose, that it's often the simplest questions that can end up being some of the most difficult to answer. Clearly, the fact that the universe implied by Newton's understanding of the laws of gravity and the universe implied that looking up into the dark of the night sky contradicted the observations that he had made and the theory that he had constructed for the universe. This was a major flaw in early theories of the universe, and making them compatible with theories of the gravitational force. But in Einstein's general relativity and the cosmology that flowed from it, there was a resolution to Olber's paradox, which we'll come on to later on. So Einstein derives these equations in which matter tells spacetime how to curve, and then realises they can be applied to the universe as a whole. Now, one of the difficulties I have with this show is that I can't show you equations in an audio format, so I can't show you how things work mathematically nearly as easily as I would like to. I think that the only real solution to this when I bump into something like this that has to be explained mathematically is to come up with a video where I go through the equations and stick that on our YouTube channel. So I'm going to give that a shot for this particular case because I think the fact that you can explain and explore the entire history of cosmology and our universe with some quite simple equations is so beautiful that frankly I don't want to let the mathematics be a bar to exploring it in the detail that it really deserves. This video won't be anything too fancy, probably just a set of slides, but I will link to it in the show notes and on social media and so on. Here in the audio-only podcast though, I will stick to a more wordy description. When you apply Einstein's general relativity to spacetime as a whole, you get a couple of equations that relate a few different quantities together. First though, you have to make an assumption, and this is the assumption that we talked about in the last episode, which is of the cosmological principle. In other words, you have to assume that spacetime is homogeneous and isotropic. This is just a fancy way of saying that on large enough scales, spacetime looks the same in every direction you look, and it looks the same from whatever position you're in. This is a massively helpful assumption because it rules out all kinds of weird and wonderful geometries. You could imagine a spacetime if you wanted to that is quite frankly bizarre. Maybe over here in this patch of the universe it twists into strange knots and loops, while over in this other location it's completely flat. Perhaps when you look in one direction you'd see this dense and weird topology with four-dimensional spacetime twisting around in all sorts of strange directions that change how matter would move through it, and in other locations it's smooth. The cosmological principle, though, rules out all of these different assumptions and basically limits you to a few different kinds of universe that you can have. These are the different kinds of universe that you can have because they satisfy the cosmological principle, the idea that space and time will behave similarly, whatever location you are in the universe, and that it will look the same in whatever direction you look on a sufficiently large scale. So under the cosmological principle assumptions, you can have a totally flat universe. You can have a spherical universe with a certain radius of curvature. If you imagine walking around on the surface of a perfect sphere, you'll see what I mean about this satisfying the cosmological principle, in the sense that you can look in any direction and see the same thing and so on. And you can also have what's called a hyperbolic universe, which is basically a universe with negative curvature, something shaped a little bit like a saddle, which also satisfies these principles. So you can imagine these as being the basic shapes of the universe that's totally empty and satisfies the cosmological principle. We can have a flat surface, a sphere, or a saddle. Then when we add stuff into the mix, matter and energy that has an influence on gravitational forces in the universe and twists space and time, that's when the initial shape of the universe gets distorted. The equations can tell you how such a universe will behave if it's curved, or if it's filled with matter, or radiation, or some other kinds of substance. But what the equations can't do is tell you what the universe actually looks like. For that you need to make some more assumptions, and you want to make these assumptions based on your best available evidence. When Einstein first realised that he could apply his equations to the universe as a whole in 1917, it caused him a great deal of concern. His view, in accordance with most of the cosmologists of the day, was that the universe should be static. In other words, there's no expansion, no contraction of the universe. The things within it might evolve, but the fabric of the universe itself should stay the same, eternally. He struggled to find a solution to his equations that allowed for this to be the case. In most solutions to the equation, it seemed like the universe should evolve over time. And we're coming back to the things that Bentley and Newton were worried about, the idea that gravitational influences or other influences might make the universe evolve over time. But Einstein, philosophically, simply did not think that this was the case. So he fudged it. You can add another term into Einstein's equations without breaking the laws of physics. And a way to understand this is to, if you can think back to when you did high school calculus maybe, when you did integration at school. When you integrate a function, you can always add an extra constant term. When you differentiate it, that term will go away, regardless of what it turns out to be. This invariance, as we'd call it, arises from a type of symmetry in the equations. So I'm going to explain this a little bit more. Consider a straight line, where the equation might be y equals 2x plus 3, the kind of thing you would have to draw in your graphing paper all the time. When we differentiate this, we find just the gradient of the line, which is 2. But the gradient of the line doesn't care about the intercept. Therefore, the differential equation dy dx equals 2 can describe any line with gradient 2, regardless of where it is on the axis and what the intercept is. You can imagine moving the line through space. You'll always have that same gradient too, regardless of where you translate it in space. And so again, we come back to this idea in physics that you have symmetries. The line is symmetric when you shift it through space. And also invariances. So you can add whatever constant you want onto the end of that and it disappears in the differentiation. Now it turns out that Einstein's field equations for general relativity are basically differential equations. And they have similar symmetries which allow for a similar invariance. So this basically means that when you try and integrate up Einstein's equations to get to a universe, there are certain constants that can drop out of these equations and you'll get the exact same universe, but these things can also exist. So speaking technically now, Einstein realised that the general principle of mathematical covariance of his theory allowed for two general covariant objects: the Ricci curvature, which describes how matter tells space how to bend, and the volume of space-time. And this meant that Einstein realised that he could add in a constant term so long as it was proportional to the volume of the universe, the volume of space-time. Einstein discovered that if you added another term into his equations, a so-called cosmological constant term, like that constant of integration, the laws of conservation of energy and momentum could still happily exist. It didn't break any rules, although it was an extra assumption about how the universe would behave. And it allowed Einstein to solve the equations for a static universe, which is what he existed at the time. So it's like we have that line, and we want to add a certain constant of integration onto it so that it goes through a particular point. Einstein believes that the universe should go through this point, that it should be a static universe. And so he picks the constant so that it perfectly balances out the tendency of the other part of the equation to cause the universe to change over time, and give him a static universe. Now you can see, obviously, that this is not that satisfying philosophically and physically either. You can see the contradiction here. Either Einstein has to accept that general relativity and his equations can't really describe the universe, which he believes to be static. Or he has to say, well, my theory only really works with a universe that's changing over time, which I don't think the evidence supports yet. So what does he do? Does he abandon the theory, or does he abandon the idea of a static universe? In the end, he does neither. He fudges the problem by adding in this extra term, this cosmological constant, which allows his theory to describe a static universe, providing you also assume that the universe has positive curvature and is like the surface of a sphere. And you can see, even in the 1917 paper Cosmological Considerations, where he introduces this for the first time, that he's not entirely comfortable with it. He says, quote, "At any rate, this view is logically consistent, and from the standpoint of the general theory of relativity lies nearest at hand. Whether from the standpoint of the present astronomical knowledge it is tenable will not here be discussed. In order to arrive at this consistent view, we admittedly had to introduce an extension of the field equations of gravitation, which is not justified by our actual knowledge of gravitation. It is to be emphasised, however, that a positive curvature of space is given by our results, even if the supplementary term is not introduced. That term is necessary only for making possible a quasi-static distribution of matter, as required by the fact of the small velocities of the stars." End quote. Einstein may have been uncomfortable with the notion of this cosmological constant. After all, it seems pretty arbitrary to have to tack something new onto the end of your theory, something unnecessary that's required for the theory to actually succeed at describing reality. Even more arbitrarily, he determined that the value of the cosmological constant must be exactly that which would counteract the force of gravity to yield a precisely static universe. And you can see why this is so annoying. I mean, you have to add a new bespoke term to your nice symmetrical equations just to get them to describe the universe. It seems like a bit of a fudge. And indeed, other theoretical cosmologists who moved on from his work were happy to come up with solutions that described universes that weren't static at all. Only a few months after the publication of Cosmological Considerations, the Dutch astronomer Willem de Sitter noted that the addition of the cosmological constant term to the field equations allowed for an alternate cosmic solution, namely the case of a universe with no material content at all. In this paper, De Sitter replaced Einstein's three-dimensional matter-filled universe of closed spatial geometry with an empty four-dimensional universe of closed space-time geometry. Einstein was greatly perturbed by De Sitter's model, as the existence of a vacuum solution to the universe was in direct conflict with his understanding of how the universe should be. Is it possible that there could be a universe that would exist, despite being totally empty of everything? A long debate between the two physicists ensued. However, we find little evidence in Einstein's writings that he accepted De Sitter's solution as a realistic model of the universe. Einstein may not yet have believed any solution to the general relativity and cosmological equations, aside from his own, for a flat and static universe could be real. But of course, this is where Hubble's observations come in, and observations once again shape how theorists develop their theories. Because what Hubble saw in the 1920s demonstrated for a lot of cosmologists who were working with this new theory of Einstein's, that the universe was not static, but expanding, and that those models of the static universe needed to be rethought. Next time then, we'll bring together those two strands of inquiry, and we'll talk about how theoretical cosmology developed in light of the new insight from Hubble's observations. Thank you for listening to this episode of Physical Attraction. Remember, you can find us on the web at physicspodcast.com. There you'll find the contact form if you have any comments, questions, concerns, extra things you'd like to know about this, explanations that need refining, all that sort of thing. Please let me know there. I try and respond to all of the emails I get. You can follow us on Twitter at PhysicsPod, and on Facebook we are Physical Attraction. We have a subreddit, not often used, reddit.com/r/physicspodcast. So there are many ways that you can engage with the show. You can support us in a number of ways too. Of course, leaving a review on your platform of choice is very helpful for us, as is subscribing to our Patreon, where you'll get access to all of these episodes early and bonus episodes as they are created. You can also support us with one-off donations by PayPal. The link for that is on physicspodcast.com. But the most universal thing you can do that will help out the show is to tell other people who might be interested in this stuff to give it a listen. Until next time then, please do, take care.